Good morning, everybody, and thank you for coming to my talk. As I sort of put a massive disclaimer on the write-up for this, there will not be very much C++ content in this talk. So if you're after a ton of C++ and very important features of C++, you've got time to leave and find another talk. But this is mainly a talk about a JavaScript hobby project of mine that went out of control. So I'm going to give a sort of overview of what this talk is going to be about. The first part is a sort of introduction about some of the history of Compiler Explorer, how it came about and where it is now. And I'm going to take this opportunity here as well in front of you. I'll have a captive audience to talk about some of the hot features. Couldn't think of anything better. Some of the features that perhaps you don't know Compiler Explorer has, because oftentimes, maybe a couple of times a month, someone will email with a great suggestion for a feature in Compiler Explorer, and I'm often able to reply with a link that says, we already have that, you just couldn't find it. So our user experience design is lacking. So hopefully if I show you where they are, you can go out and show other people what these great features are. And then I will actually get to the real subject of the talk, which is the behind the scenes, how it works, and hopefully you won't run away screaming and never use the site again if once you know how it actually works behind the scenes. So a little bit about me, which kind of explains the origin story of Compiler Explorer. My career has been mainly in sort of high performance C++. I spent a decade making video games, which was a lot of fun. Then I sort of set up a company to develop C++ tools. I worked then up for Google, where I worked on the YouTube mobile client, like in the early 2010s or late 2000s, back when maybe mobile phones weren't really performant enough to do video, but we were trying to do it anyway, so it was a lot of fun. And then I've spent the last decade in finance. So the theme running through all of this is fast and C++. But then this happened to me. So I got verbed. And you won't hear me referring to it as the name that I know many people refer to it as, but it's Compiler Explorer to me. And it has changed like the path of my career and the path of my life in a lot of ways. So let's talk about how it came about more specifically. So in about 2011, 2012, I was working for a trading company in low latency. And there, every sort of last bit of performance is important to us. And we were writing most of our code in C++. And around this time, obviously, C++ OX was starting to come out, C++ 11 as it ended up being. And we were sort of asking ourselves the question, there are these cool new language features, range fors and lambdas and things like that, but we don't understand the performance impact of changing our code from regular for I equals 0 to vector.size to a range for. And so a colleague and I sat down, and with this very simple little bit of Unix script, we came up with a little program. So this is, if you don't know Unix, the watch commands just runs the command that it's passed in the quotes every 2 seconds and just keeps replacing the screen with the results of it. And so we ran a compiler, we passed the new flag C++OX, we piped it through C++ filt, which turns all the horrible mangled names that come out of the compiler back into readable C++. And then that grep there is just a filter, a very, very cursory filter that removes any of the crazy assembler directives. And what we ended up was something which looked not a million miles different from this. I split my screen in half using tmux. I ran VI, the one true editor, on the right-hand side. Yes, this is how I get you on side. And then on the left-hand side, I had that command running. And so I could just edit the code, and I could save it, and I would see immediately the impact. So we were able to take snippets of our code and do what we all sort of take for granted now, is just chuck it in and see how it comes out, right? And it was just so enormously powerful and we were surprised how fast the compiler ran when you give it a small piece of code, because I mean, I'm sure all of you feel that your compiler is like the slowest thing in the world, and that it takes forever. So I think people don't think that you could run a small experiment with a bit of code and get something interactive. So that was great, but it's not very pretty, I think you'll agree. So fairly soon after, also as part of my job, I was working on some internal tools that had like websites associated with them, so I was kind of cooled down with the kids with my HTML skills, and I thought, I know what I can do. I can write this on the web. Oh, if my clicker worked. And so this is the very first version of GCC Explorer, as it was called back then. And as you can see, it's pretty familiar. There's a lot of things there that are still on the site today. And in fact, if you go to the GitHub for Compiler Explorer and check out the very first commit, give or take a couple of things that had to be corrected to make them work in modern JavaScript, this is what you get. It still works. And a lot of the features that you recognize are there, but some things are missing as well. Like there's none of that nice coloration in the background that links the input C code to the output C++ code. Input C++ code to the output assembly code on the other side. There was a very limited number of compilers, and they were all GCC, hence the name. There we go. So how has it evolved over the years? So in the first couple of years, it was pretty quiet. Not that many people knew about the site. It was stood up, but it was mainly just me and a couple of people I knew that used it. We added coloration and filtering pretty soon on, and obviously compilers were added, which started to add grist to the mill for those people. Once I put Clang on there, they're like, "Why is it gcc.godbolt.org? You've got Clang as well." I'm like, I suppose so. We added new languages like D and Rust, and we started making short links using goo.gl. And we had to recently overhaul our link shortening service because Google have sunset goo.gl, unfortunately. So a little story about the way that the D language support went in. That was actually the first other language that Compiler Explorer supported. So Andrei Alexandrescu was visiting my company giving a talk on performance, and I was in the audience, and we were sort of like, there's a bit of fun banter between the two of us. He didn't know who I was, and I wasn't anybody back then, right? Still really not. And then towards the end of the presentations that he was giving, he said, actually, I think there's some kind of website that you can type your code into and see how the assembly comes out. And like all my colleagues start looking at me, and I'm sinking into my chair. I'm like, oh, yeah, that's my website, actually. So we had a good chat about it. And at the end, he said, actually, would you mind putting in D language support? I want to help proselytize that language. And so that's how d.godbolt.org came about. Incidentally, at this stage, we were still using different subdomains for each of the languages that we had. And d.godbolt.org exposed a whole bunch of interesting bugs in all the tools that we were using, like Docker, for example, because single character name things would break stuff. And just another thing, like normally it's like longer things cause problems, but shorter things can cause problems too. So that's the first 2 years. The next 2 years, we added binary support. This is not executing your code. This is actually just compiling it to binary and showing you like the opcode. So the disassembly view also has like the 0E, 0A that the CPU actually sees. We moved from that sort of fixed view that you saw in the example of just the two panes next to each other to something called Golden Layout, which is essentially a window manager written in JavaScript that runs inside your browser. And that allows us to have those panes that you can drag and drop around and reconfigure and resize and all of those good things. We changed our editor from an open source, well, the Monaco's open source as well, but from, oh gosh, I can't even remember what the previous editor was now, that's terrible. We changed the editor from one thing to another one, which was the Monaco. And Monaco is Microsoft's Visual Studio .code editor. So if you've used VS.code, that's actually the same editor that you use when you're playing around in Compiler Explorer. And that gave us a bunch of new features, including a diff view. And we started adding support for libraries so that if you were using Boost or other sort of third-party libraries, you could see how your code came out by including those. That started a whole can of worms, incidentally, because there I was sort of saying like compilers are fast. You get quick feedback if you have a small snippet of code. That starts to change if you include Boost all.h or whatever. In 2018, so this is last year, we finally unified the languages. So by this point, we had a dozen languages, and having a dozen domain names and a dozen Docker containers and a dozen rules all over the system to route your web requests to the right spot was getting overwhelming. So now if you just hit godbolt.org, you get a pick of compilers. You can pick anyone you like from the dropdown. Sorry, a pick of languages. And Microsoft came on board. That was a really big uptick for us. Microsoft actually administrate and run a separate site, godbolt.ms, and we shell out to them to get the Microsoft compilers. So the official Microsoft compilers, not the ones that have wine in parentheses after them, they're actually going off to a Windows host managed and run by Microsoft, and the results come back, and we kind of just proxy it. That's a mixed blessing. It means that we get a genuine Windows compiler running on Windows and not some dreadful wine hack, which I really don't want to go into the details of to get the compilers running on Linux. But it also means that we have to liaise with Microsoft in terms of like feature stacks and things like that. So it's a little bit out of the loop. And I am, as you'll see later on when I talk a little bit about how the site is administered, you'll see that really I'm not qualified to do any of this, and I'm even less qualified to do administrate a Windows system, which is allowed to run arbitrary code from anyone who's typing stuff on the internet. So thanks to Microsoft for that. We also added tools windows. And this year, of course, the big ticket feature, the thing that everyone has been asking for since the year dot, right, is, no one? 6502 support, right? Yeah, no, okay. It's code execution. So I've actually met a couple of people already this time, at the conference, for whom I don't think realized that you can now actually execute your code on the live site. We'll go into that in a little bit. Excuse me. I think I'll take some water. Okay, so that's like how we got to where we are now. And so I'd like to show off some of those features that I've been talking about. So the first thing is that execution support. Now we have to cross our fingers and hope that this all works. Yay! All right, so this is a local build of Compiler Explorer. And for anybody in the room who is wants to use Compiler Explorer but currently can't because they're worried about sending their code across the internet, which is a very real and relevant thing to be worried about. It's really simple. In fact, why don't I go up here and go over to here? I just literally type make in this directory, and that's the Compiler Explorer backend running on my laptop here. So it's pretty straightforward to do. You have to have a few compilers installed, which you probably already do, but it should just be the case of typing make. And if it isn't, send me an email or drop us a line on the Slack, and we'll make sure that it's easy to do. It's really important to me that although we have the public site, that you can use the tools yourself locally and feel confident that you're not exposing your trade secrets to me. And for what it's worth, I don't read your code. We don't have time to look at anything that happens, right? There's nothing there. Okay, so this is execution. So I've got the world's most trivial Hello World program that we've all seen and loved. And yeah, unsurprisingly, when I tick this .a.out box here, which again, our user experience is not the clearest. It makes sense to me that ./a.out means execute the binary, but for many other people that may not be quite so straightforward. So that's the execute. And indeed, we see not only do we see that the compiler ran and generated all the wonderful disassembly that I love so much, we actually have the output of the program here, which is pretty cool. Now, oftentimes, of course, you want to do more than this. You might want to pass parameters into your program. You might want to pass like a string on standard into your program as well. And also very often, you're not actually interested in the output of the assembly. You just want to run the code. And I mean, obviously that disappoints me as a lover of reading assembly output, but some people I know don't like it as much as me. So one thing we put in fairly recently is a view that is execution only. So I'm going to drag this over here. And now we just get the output from having compiled and run the program. Behind the scenes as well, you're actually doing us a favor. There's half as many requests that are going on. We have to sort of call the compiler once to say output assembly, and then we filter it all. And then another time to say, no, actually compile, link, and generate a binary. And then we have to run it. So it sort of reduces the load on us. But indeed, here is hello world again. And of course, what we would like to do is make it slightly more interesting. So if argc, never do live coding incidentally if you want to have a stress-free presentation. Hello. And then we're going to just say, we need a comma there, of course, those be grammatically nice. argv1. Now, or else, and it wants to put the bracket there, and we don't want it to put the bracket there. So another sort of hidden feature while we're here, if you right-click, you'll see that we actually can't do support formatting. I realize that's not very clear on the big screen there, but I can run it through Clang format, and it will reformat the code, and you can go into the settings and change what formatting it looks like. So you'll find me hitting Control F9 all the time to just reformat my code as I go. So anyway, if we've passed in 2 arguments, we're going to find out, we're going to see what arguments were passed in. So I can click up here, and the little box comes down, and now I can say CppCon, and hopefully that just comes out. So we can add inputs there. We can also, if we don't care about the compiler, we can get rid of it. We can add the standard in. I can type a load of stuff in here, and if I was bothered to write the stuff to read through standard in, we could. So that's pretty cool. Also, as I say, it reduces the amount of load on us. And if you're trying to share a link with someone and the assembly would otherwise be a distraction, this is probably the view for you. So the next thing I'd like to talk about is the unified languages. And of course, there is a certain amount of caveats that I'm going to put on here because there is a very cool, I realize there's a certain amount of ballsiness putting a Rust code up in the C++ conference, but this allows us to compare and contrast languages. And I would encourage you to do this, where if you want to see what else is out there and how the code generation might differ. But please don't start holy wars on the basis of my compiler is better than your, my language is better than your language or whatever. So use this wisely. So I'm actually going to add a new editor down here, and I'm going to change. Oh, it's already in C++. And then from this, I'm going to add a new compiler, and then I'm going to pass the same-ish compile options. And we can see that, yes, squaring a number in both languages amounts to essentially the same thing. Now, if, like me, you aren't very good at spotting subtle differences in two otherwise very, very similar things, one thing you may not be aware of is that we have a difference view. And if I click the right thing, it would help. So I can drag this. I'm going to put it over here for now, but I'm going to maximize it. There's a wee button at the top of each of those little windows to maximize it. And now you get to see the actual difference between the two implementations side by side. It's like a unified diff, or a side-by-side diff, I should say. And you can see, apart from the compiler sort of slightly disagreeing on the instruction ordering, they do exactly the same thing. That's not true if you start doing some other things that have overflow, because for example, Rust will check for overflows, whereas C++ will happily let you overflow all you like, and it's just UB. But that's the difference there. I haven't got time to go into that one, but we also have views. So a view is an extra pane you can add on after the compilation to sort of further process the output from the compiler and give you useful views, useful information about it. So this is one of my favorite little pieces of code that gets optimized. I know I've shown this before at other talks, but how often do you find yourself thinking, I wish I knew how many bits were set in this integer, right? I bet that happens all the time, right? Yes, there is. So some of the hardware and firmware guys are like, yeah, that's more likely us. But it's also really useful for things like packed structures and other cool data formats. So it is useful, although it seems sort of slightly like an unfair programming question to ask in an interview. But if we look at how this comes out, this is where the coloration is really quite sweet, actually, because here the int count equals 0 corresponds to that XOR EAX pretty clearly, and then this stuff here is to do with the loop, and then that count plus plus is the int construction, and then there's this strange but unattributed, because it's not perfect, BLSR instruction. So I'm just going to mouse over it. This is another thing that people aren't necessarily aware of, and I was really surprised when someone said, oh, I didn't realize you could do that, because I do it all the time and it annoys me more often than not. If you mouse over an instruction, for x86 at least, it will give you a little short version of what that instruction is. And if you need a little bit more help, you can go to the context menu and say, no, I need more information, and you get the whole of it. And even if that's not enough, you can go over and click the documentation link here, and you go to Félix Cloutier's website, which has all the information in the world about what that is. So this is reset lowest set bit, which is a pretty cool, oops, have I opened it in a different new window? Yes, phew, all right, I just got myself lost there. It's a pretty cool trick that the compiler has done. It's realized that this funny little thing over here, value and equals value minus 1, is just clearing the bottom bit in the integer. And it's got the instruction to do that. That's pretty smart, right? Actually, for those, if you've never seen a little bit twiddly trick like this before, to clear the lowest set bit, it's fun to sit down and write it out in binary and work out why this works, right? I encourage you to do it. All right. So that's all cool and that. And what was I showing you? Oh, yes, right. That's right, the view. So I'm going to add a view that is graph output. If I plop this over here and then full size it and hope that it works. Oh, zoom. Where have I gone? Oh, dear. Never do live demos. Oh, there it is. Okay. So we have a little bit of a problem there. But here you get to see like the basic control flow structure of that assembly output. We've got the little snippet at the top, which is like the beginning part. It either jumps out to the ret at the end, or it jumps to a block, which is then repeated multiple times for each time it's finding a new bit to count, and eventually ends out in the return there. So that's kind of an interesting way. If you're not so familiar with assembly instructions, you might be able to at least sort of get some idea about the sort of vague structure of the output program, which may be quite different from the input. For example, if I switch to a different, just as a caveat here, I very carefully cherry-picked the exact version of GCC that I used here to make it show my point. Because if we go to GCC 9 or Clang since forever, you'll see that far more cleverly, the compiler is able to realize that there's actually an instruction which does the entire thing, right? It just counts the number of set bits, which is pretty cool. And obviously there, it's very clear and obvious that there are no loops whatsoever going on in the right-hand side in that view. Just as an aside, and because I love this stuff and I've got a captive audience, the interesting thing to me here is that GCC puts that XOR EAX, and for that's essentially saying result equals 0, and then the second instruction is result equals number of bits set. And you're like, well, why did you do result equals 0 first? Surely you were about to overwrite it. And Clang doesn't do that. Let's have a look. Clang trunk. Oh yeah, another sort of top tip. You can hit backspace in this little drop down and you can type substrings and you can find compilers, because when you have hundreds of them, it's hard to find. So Clang doesn't do that trick. It just says, well, we'll just count the number of bits set and put it in the result. Why would you 0 it first? And this comes down to a bug in the CPUs, Intel CPUs, until very, very recently, have a false dependency. They think that the population count instruction needs the previous value of EAX before it can start running, which is not true. It completely overrides it. So the workaround that GCC puts in is to sort of set it to 0 in a way that the processor goes, oh, I guess that's completely divorced from any previous version of whatever was in EAX. So it's pretty cool. To me. Maybe not to you. All right, yeah, we're going to get into more of this stuff. This is my favorite thing. This is the LLVM MCA tool, which is the machine code analyzer. So we have a simple-ish function, which is just summing over an array here. We're going to start at the first element, and we're going to just add up all of the elements and return them, and they're all unsigned integers. And do not peek behind the curtain and look at this horrible bit at the top, which didn't appear in the earlier bit. That's just to make the compiler generate slightly less code. But the cool and interesting thing is just looking over here and going, wow, how clever are compilers these days? It's using all these very scary VP added things, which I could mouse over and get all the instructions on and whatever. But I wonder how fast this really is. Now, of course, the one true way to find out how fast this is to run it and benchmark it. But benchmarking is hard, right? So we can at least get we can intuit something from this. But I'd have to kind of get the Intel manuals out and work out how, this is the core loop here, this L2 thing here. This is the bit that's doing a lot of the adding up, and it's doing them 32 bytes at a time. So it's done some vectorization, some clever things going on in there. But I don't know how slow this instruction is. I don't have any kind of intuition about whether it's fast or otherwise. And as it's an accumulator, right, it depends on the previous iteration of the loop. So maybe if it's like really slow, then each iteration is going to take as long as that instruction does. But I know a tool that knows that more about it. So I'm going to add a tool that is the LLVM MCA, and then I'm going to maximize it here. And LLVM MCA analyzes the output from the compiler, and it uses LLVM's own internal representation and understanding of how the CPU will actually execute the code to determine some statistics about how your code will perform. Caveat here, it is not perfect. It is far from perfect, but it's a really good starting point for your understanding about how the CPU really actually runs. So here we can see, oh good, we can actually see the far extent here. That often gets cropped off. Here's the code as the CPU would see it. And in these different columns here, 1, 2, 3, 4, 5, are different things about the instructions. There are the number of micro operations. So even if you think the assembly code is the most basic block, the CPU breaks it down into even smaller pieces of work to schedule and do clever things with. So most of these are a single micro operation, which is this small part of work, and most of them have a latency of 1, which means that their result is ready after 1 clock cycle. So that's pretty cool. And then this reciprocal throughput here on the third column here gives you an indication of how many of that instruction that are unrelated can run at the same time, or rather can start at the same time. They can be running multiple. So this 0.25 means that 4 MOVs can start execution on the same clock cycle, which is just bonkers, right? These things run at 3 gigahertz, which is like a third of a nanosecond per clock cycle, and they're scheduling and issuing up to 10 instructions every single clock cycle. It's just insane. And then if that's just one core in there, there are a dozen cores in some of these machines. It's amazing. We live in amazing times. But then let's look down at that VP add. That has two micro operations, and I happen to sort of know that that's because this is both doing an add and it's doing a memory operation. It's fetching the next set of inputs here in this YMM picture RDI. So it's separated the read from the actual add, which is cool. They can be scheduled independently. But then the horrible thing here is this 8. It's got a latency of 8. So given that it is reading in 8 or 32 bytes worth of ints and then adding them to a totalizer, you might imagine that it would have to wait 8 cycles for the previous one to finish so that it can add to the current accumulator. Now we can't tell that from this view. And in fact, the fact that the whole code is present means that it's hard for us to intuit much more from this. We can get some just overall statistics about which units on the CPU are likely to run each instruction. But really what we want to do is analyze that loop here. So I'm going to copy-paste that loop, and I'm going to put it into our pseudo-language analysis. And what analysis allows me to do is paste in the code directly and run just LLVM MCA on the code that I chose. Now, there are definitely ways to do this. You can put little pragmas and ASM trickery to hint to the LLVM MCA, can you just look at this piece of the code, please? But like anything, when you start putting ASM volatile in the middle of your critical loop, then sometimes the optimizer decides to do different things. So this is a great way of just zoning in on a loop. And then if I put dash timeline, and I'm going to tell it what CPU I've got as well, Skylake, and then maximize this so you can actually see. The coolest thing, so this is all the same, it's just syntax colored because of reasons. This is my favorite thing in the whole world. This shows, and at this point I would annoy the cameraman by dancing over and pointing up at things, but I'm going to give him I'm going to use my mouse pointer instead. Time is going from left to right, instructions are going from top to bottom, and the iterations thing that I put on said, just assume this is a loop that's going to run 100 times. And what you can see is on the first clock cycle, or the 0th clock cycle, all 4 instructions were decoded. On the second clock cycle, the add, the VP add, and the loop counter add started running. But the comparison was stalled because it needs the result of the add. So that's got an equals there. Likewise, the jump if not equal was stalled because it needs the result of the compare. On the third cycle, we are still executing, that's the 8. The 8 lowercase e's here, or the 7 lowercase e's here, are the latency of this instruction. And the capital E at the end means, and it's ready, it's finished, and if somebody needs the results of it now, they could start running. So we can see that there's the long instruction here, but look, down here, these other instructions, the add, the compare, and the jump, have already finished before the VP add has even got halfway through. And if we scroll down, we can see that actually the next iteration of the loop, and in fact of 7 iterations more, are already ready and started running. And the question that I had, which is there a dependency between the VP add and the next one, is no, there isn't. You can see this VP add down here, oops, if I could select the whole line, has started running 1 cycle after the first one. It's just amazing. It's what the hardware's doing beneath us, unaware of us, is amazing, absolutely amazing. Anyway, and I could talk about this forever, but I don't have forever. I have 31 minutes. So let me close this. And, oh, I think I can close the whole thing now. Oh, no, not the whole thing, Oh, dear. This is what happens, sorry. P, C, E, oh, why aren't you completing now? There we go. Phew. Right. Did that one? No, we didn't. It's finished. LLVM MCA. Conformance view. Aha, phew. All right, we're back on track. Sorry about that, everybody. Nothing to see here. How often have you... so who here has to deal with more than one platform or compiler? Yeah, it's a pain, right? Especially if you want to use the cool new features that are coming in the language, and you want to say, hey, I want to use std file system because, frankly, I'm done with using Unix or hash if def Windows, something. But you're kind of scared because maybe you've got 5 compilers that you have to support, and you're never quite sure which features are available in which compiler, or whether template trick X resolves correctly and compiles your code or not. So that's what conformance view is for. So this is not a replacement. This is not a tool that runs on the back of a compile, an existing compile. It's a complete replacement. So at the moment, we've just got a regular standard file system using a bit of code, and yeah, sure, it compiles all these flags. I'm going to steal those flags, and I'm going to kill the output and add a new, not compiler, not execution only, a conformance view. And what the conformance view looks like is this. I can add a number of compilers. I can paste in the... See, we're going to work on usability. There, seamless. And I can pick a compiler for each one of these. Say, let's do GCC 9. And let's do GCC 8.13, sure. And GCC 7.4, sure. Yeah, oh. This is the first one that's failing, right? We little green box up here means that it compiled okay, and the little red box means it didn't. And we get the error is hiding over here. And if we actually want to go and dig in more, we can click the button here, and it will bring up a view just like you'd had your own view to start with, and you can like fiddle around with the settings in there. But what this is really useful for is obviously you fill this up with all of the compilers that you're interested with, and then you can tinker around in this view here. And like for example, the way to make this compile on GCC 7.4 is to just comment it all out. Now everything passes, right? So that's fine. No, there are some things you can do with std experimental and stuff, but I don't have time to go into. But hopefully this will be a useful tool for those of you that have to suffer through writing code that has to compile on multiple compilers, multiple settings, and multiple platforms. All right, but there's a lot more than this. So this is a small list of some of the other features that I haven't got time to go into. One little known, and for a long time I hid this away from everyone because it's a problem, really, is that I support hash include and then a URL. Now, it doesn't work very well because I haven't done a full preprocessor. It happens on in your client, so every time you hit build, it's actually going to fetch that, bring it to your local machine, and then post the whole thing up to Compiler Explorer, which is a bit of a pain, but also prevents us being used as a sort of denial of service attack vector where people just hash include google.com 1,000 times and then like compile it or whatever. But unfortunately, it doesn't resolve includes that include needs. So if you just pointed at like boost.h in some GitHub repo somewhere, and boost.h needs boost/internal.h, it's not going to find it. It's going to look on your local machine, and that won't work. But it's there. It's useful for like a little snippet. If you just make a GitHub gist of like a library set of library functions, you can paste it at the top, and then you can demo the thing that's most interesting to you. Which actually, while we're here, for another reason to run a local Compiler Explorer instance is so that you can do -I and then /home mat my source project, and then you can include files from your own project and just look at the bits that are interesting to you. We've got a whole bunch of other tools. There's Clang Tidy, Clang Query. PA hole is something which will analyze the binary that you generate, and it will tell you if there are holes in your structures. So if you've done bool double in a structure, you realize that you're wasting like 14 bytes worth of padding, and it will give you an alert that tells you about that and say, hey, you probably could switch the order of these things, and it would be a smaller structure. We've got readelf, which will look at the sort of like what the compiler tagged in the elf at the end. Of course, Jason's keynote from 2 years ago, whenever it was, with his Commodore 64 trick where he like context brought up a whole Commodore 64 game and then used a C++17 conformant compiler to generate x86, and then he wrote a very simple tool that takes the x86 and maps it to 6502 opcodes. We have that support too, which is cool and fun. It doesn't support very many actual opcodes. The 6502 support I alluded to earlier, by the way, that means if you go to the C section, you can actually compile to directly to 6502 if that is useful to you, which I would be very surprised if it was. It's my other hobby project. And then there are some really interesting views, which I meant to demo, sorry. I've missed them out, but I'm also going much slower than I thought. So you can look at the internals of both GCC and Clang. So GCC has a view you can drop down and see like the various stages within the compiler and its output. And there are like 200 different stages, which, I mean, when you sit down and think to yourself, gosh, my compile took a little while, have a little bit of respect for the fact that it's gone through around about 300 different transformations to take your code and slowly convert it into optimized output, assembly output. You can also look at the Clang intermediate representation. So that's the LLVM IR. And we also support actually LLVM IR as an input as an input language. So you can actually paste in LLVM IR and tinker with like the opt settings that it allows you to play with. And if you're doing like very complicated templatey things, first of all, thank you for doing it so that I don't have to. But you can look at the Clang parse tree. So if you've got something which doesn't appear to be parsing very well, or parsing differently to the way you expected, there's a view that shows you LLVM's internal parse tree. All right, the actual behind the scenes bit. Now I've tortured you with all of the other bits. So I have actually got a picture. I know it's be surprising to you. I've got a picture of one of the servers that runs Compiler Explorer. There it is. All right, now that's a BBC Micro. Who here knows what a BBC Micro is? I know there's a couple people. Yeah. Wow, that's a lot, actually. Gosh. So a couple of years ago, I did a talk here about emulating a BBC Micro. It's my favorite little program, computer. Anyway, but more boringly than running a BBC Micro, it runs in Amazon like everything does. It's written in Node.js, as I said, which is server-side JavaScript. And if that sounds horrible to you, spare a thought though for JavaScript developers, because all of the weird corner edge cases of C++ that we've kind of learned to internalize and kind of go, well, just don't do that. JavaScript also has them in spades. You're adding a string to an integer sometimes turns the integer into a string, and sometimes it doesn't. It's just But it's pretty good for writing websites. It's very asynchronous, and it was at least past the resistance at the time that I started writing, and now we're stuck with it. So it runs on Amazon Web Services. There's a whole bunch of load balancing stuff that goes in front of it. We're usually running anywhere between 3 and 5 actual virtual machines to deal with the load. And I don't know how many we've got at the moment, actually. I didn't think to check, but I imagine the number of compiles is up a bit as we're all sat in or maybe it's down because I can't actually see any of you on your computers, so maybe we've just reduced the number of people that would be using it. And it uses some Amazon technology. And here is the single worst picture I've ever made in GraphViz. I mean, and it takes a bit of effort to make a bad picture in GraphViz, but it gives you some idea. There's you at the top, the outside. You hit CloudFront. CloudFront is an edge cache. So Amazon support this thing where we can store all of our static data in a way that gets shipped out to data centers near you. So for all the things that don't change that often, and in fact, even more so recently, right, we've made that a little better, there is a copy of that data on the edge. So hopefully that means that the page loads quickly. Doesn't help you for the actual compilation, of course, because that still has to be sent to our computers to be done. If it doesn't hit the cache, it goes through to a load balancer, and the load balancer is responsible for working out what kind of information it's serving up. We have 2 other sort of instances of the site. There is a staging site and there's a beta site. So we use the staging site to sort of kick the tires with a new release to make sure that we aren't about to unleash something which is absolutely broken upon you all. And I mean, hopefully the site's been relatively stable. Despite all the things I'm about to say about how horrific it is behind the scenes, most of the time it's up. So, but we do check out stuff in staging because there have been mistakes made, mostly, almost exclusively by me. And then when we're trying out longer term features that we're still working on, we'll put them on the beta site. But most of the queries will hit production, and there it goes to a bunch of nodes, and that number of nodes scales up and down depending on how much load we have on the system. So it can be as few as 2 and as much as, I think, 7 that we can have there. We've never hit 7. It's just surprisingly few resources are required to run the site, all things considered. And then behind all of that, we have some instances, one for administration, that's the one we log into and actually do like poking around and setting up the releases and whatnot. And then we have a giant compiler builder instance, which we turn on just to build all of the compilers. And then magical things like DynamoDB, S3, and EFS. Some statistics, this is slightly out of date actually. I should have updated because we had our biggest week last week. We had 1.177 million compiles in a week last week, which was quite something. But as you can see that the trend, it's not quite a hockey stick, as a friend of mine pointed out, but it's, we're doing a fair amount of traffic. And obviously the new thing, execution, you can see it's very dependent on what day of the week it is. This is a day-by-day view. And what that sort of amounts to is, roughly 1 million compiles a week, which is about 1.5 a second. We do 4 at peak. Presumably we could probably do more than that at peak, but that's limited by the number of instances that we have running. There are 80,000 executions, and we make 3,000 short URLs. You remember I said that we used to use goo.gl. We now have an in-house solution for the links, which I'd been putting off for so long, as I don't want your data. I don't want the responsibility of holding onto your precious code and links and stuff, but we had to sort of become confident and develop our own system, and we have backups and things. And that's actually a frequently asked question of mine, is that people say, if I make a short link, how long will this last? And my hope is like forever. I really try hard, the team tries hard to make sure that nothing we ever do will cause that link to stop working. And that's partly why we have 400 plus compilers, because I've never retired a compiler, because the URL says, well, I built this with GCC, some ancient weird version you got from sudo apt-get install in like 2011, and we still support it. So there are more than 400 compilers, although in fairness, that's double counting slightly. The C and the C++ compilers are usually the same thing. And we have more than 250 gigabytes of compiler binaries. That's like 1/4 of a terabyte of just compilers. It's honestly, people ask us, say, why don't we use smaller services like Amazon Lambda and things, or why don't we just copy all the compilers onto each of the machine to make them go faster? And it's like, well, how long do you think it takes to ship 250 gigabytes to a new instance to start it up? It's a long, long time. And we support all these languages. And I'm embarrassed to say I have literally no idea what clean or zig are, and only the slightest idea what Swift is. So we're very, very lucky that we have a very active set of volunteers who contribute and send pull requests to add in their favorite languages and libraries. And I encourage you to do the same. If you're a maintainer of a library, or if you use a library, then it's relatively straightforward to add to Compiler Explorer. There's a document even that explains how to do it. I don't think it's out of date. I'm looking at. No, you don't know. Sorry. Austin here at the front is one of the people who work on Compiler Explorer with me. So I'm very lucky to have a core team of about 4 or 5 of us who are actually working on it. I'm just the surname that gives the site its name anymore, and I don't actually do any work on it. So maintaining it looks like this. We've written some scripts that actually do all the heavy lifting. So we'll log into that administration node, and then we list like instances and say how many things are actually currently running. We list the builds. So every time a check-in happens in the Compiler Explorer repository, we have a continuous integration service running in Travis. And if all the tests passed, or if the test passed, we don't have so many tests, unfortunately, then the resulting tarball is published to S3 as like a potential deployable candidate. And then once we've pushed it to the staging environment and made sure it hasn't completely broken everything, we will then do something like this, where we just set effectively a pointer that says, when a node starts up, it says, who am I? What version should I run? And it goes and downloads its appropriate version, unpacks it, and then starts running it. So an update is as simple as us setting that up value of the build number, and then just restarting all the instances. And the restart thing is smart enough to know that it shouldn't just turn them all off and then fire up 10 more. It actually slowly cycles them so that you should, in theory, never actually see any downtime. And we've actually made some improvements on that front recently, so that even more so you shouldn't see. Occasionally you might see the site as being updated thing, the banner at the top. We do put that up there just to sort of give a bit of fair warning. But hopefully most of the time you don't notice when we're completely tearing it down and starting it up again. So the compilers are built with custom Docker containers. I am a huge fan of hermetic, repeatable builds. That's my favorite thing in the world, is just knowing that I can type make again and get the same thing back out again and not be reliant on some random internet package that may have changed or is a different version now or something like that. So we have a Docker container that we use to sort of have the prerequisites for building a compiler, and then we pull down the compiler source into that and build it in a sort of repeatable fashion. So pretty much every compiler we've built ourselves, and who here has ever built GCC or Clang? That's a lot of people. That's great. Actually, I'm pleasantly surprised. That's great. But it's a bit of a faff to start with, right? There's a bit of configuration and a bit of fiddling around, and then it takes quite a long time. So yeah, it takes us about 4 hours a day to build all of the trunk compilers. So we do those, we do trunk GCC, we do trunk Clang, and then we have a number of patched versions of both Clang and GCC, that including things like the compiler that supports the Herb's meta thingamajig. What is it? Meta classes, thank you. Meta thingamajig. And it is, as I've put here, that's actually a link to our build output page. It's the world's worst continuous integration. It really is dreadful, but it works. And we tried using Amazon's own CI service, and we tried using some other services. But as you know, building a compiler, you need something really hefty. Otherwise, it's going to take a very long time. And when I got a quote for how much it would cost us on Amazon's own CI service to use their CI things, where I just sort of give it a Docker image and say, can you do this, please? It's 4 times more expensive than just firing up an instance and running make myself, which seems absurd. And I emailed them and said, are you sure you've got this right? And they're like, we'll look into it. We can help you optimize your build. I'm like, no, you can't. You really can't optimize GCC's build. I'm pretty sure some very smart people have already done that. Maybe I'm doing disservice to the Amazon here, so I apologize for anyone who works for Amazon. Security. Okay, this is a big thing. So for the longest time, we avoided executing your lovely code because as much as we love you, we don't trust you. And nor should we, really. But even so, a compiler itself is a massive attack vector. And about once every 2 or 3 weeks, someone would email me and say, hey, you can get around some of the simple checks we have and do hash include, etc. password, and now I can crack your password. I'm like, well, yes, I do know that, and B, you can't really, at least not since like 1980, shadow password files and all that nonsense. But, it definitely exposes a whole bunch of functionality. For example, I don't know if you know, but you can inject plugins into GCC with like dash plugin, and you can load an SO and basically execute it as part of the build. So I had a very plausible proof of concept attack mailed to me where someone was able to get Clang to crash, and in the error dump of Clang crashing, it printed out the real path of where we had put it in /temp, and as a result of it being in /temp, if he was quick enough, it wasn't culled. And that meant he could write a piece of code that compiled, an SO was generated, and then Clang would crash it afterwards. And then he also had the path to it, and then he could use it as a plugin for the next stage and kind of launch an attack on the site, which was very clever, but yeah, disappointingly, but so. So for a while we had some dreadful LD library trickery to try and get the compiler to not read files it shouldn't read, but that was flawed from the start. So most recently, given that we have to actually execute user code now, we're using some sandboxing techniques like this project FireGel and then Google's NSJail, which they use for their containerization. They've open source. We're going to be moving to that soon, and we'll talk about why in a second. So now we jail both the compilers themselves and more strictly, we jail users' own code. So in theory, again, I'm going to knock on wood, you shouldn't be able to destroy the site or even look at other people's code or do anything horrendous like that. That's not a challenge, but if you do find a way, let me know. And I think I'd much rather know that there's a flaw in the site than find out that somebody malicious has actually taken it. Okay, so behind the scenes, we monitor this with a whole bunch of technologies. Papertrail is the main thing that we use. Well, I use anyway. It's essentially a distributed log tailer. So I can, in fact, why don't I do it now? Why would I not do that? Let's have a look. Oh, I bet you they've changed the URL. All right, no, it's not working. I'm not going to spend any time on it. But effectively, I just get a nice view, and I can see all the logs and what's happening. It's all the posts and things going on. It's pretty much if there's someone's reporting a problem with the site, I'll look there and see if there's any kind of debug output that we've written that'll help us diagnose it. Of course, the AWS dashboard tells me the state and status of all of the nodes and what they're up to. StatHat is the log, so it's the statistics aggregator. That's the thing that you saw with all of the stats, and I tweeted out a link earlier this week. Google Analytics, some of you who were here earlier have already seen. That's useful for us to sort of track where our users are, what browsers they're using, what they're doing on the site, so we know where to focus our attention for future development down the road. We use Sentry. That checks up if you have a JavaScript error. So there's obviously a lot of code is running in your browser when you're looking. There's all the UI elements and there's the editors and things like that. If there are problems in the JavaScript code, then we catch those errors and we post them back, and that allows us to find bugs in our terrible JavaScript skills. My terrible JavaScript skills, sorry. And then Statuscape monitors uptime, which coincidentally, this is an old picture, but you probably can't read it all, but this is like the uptime and the times of down times on the site. So that, 2-minute outage in the end of 2018, an 8-hour outage, eek, also in 2018. We've had a couple of outages this year already, actually, and we've had 2 things happen recently that were rather unfortunate, but we'll talk about those in a second. So, we try our best to keep the site up. We really do. But this is not our day job, right? I do actually have a real job as well, as does everybody else who's involved in the project. So there's only so much we can do. And thankfully, I've always had very forgiving employers who know that if the site goes down, that I'm basically not working on anything for them anymore. I'm just going to be frantically hacking on my laptop to get it back again. So what has gone wrong? So yeah, in August 2018, I made what I thought was a completely innocuous and simple change to the CloudFront configuration, which is, again, that edge cache around the world. The thing about the edge cache is that there are a load of them, and it takes a long time for the configuration change you make to make its way to all of the edges, and in particular, the one that happens to be nearest me. So I made the change, and I reloaded the site and went, seems fine. But of course, it hadn't actually updated locally. And then I went to bed. And so 8 hours and 14 minutes later, when I woke up again, I realized the site was on fire, and I had to revert that change. So that was That was an unfortunate user error. This is a more complicated one, and it took a long time to diagnose. Again, this was a real one. Everything was on fire type of situation. So unbeknownst to us, our network system, where we store all the compilers, so as I said, the 250 gigabytes of compilers, we can't put them onto each of the individual computers. We actually just share all of them on a network drive, which has its drawbacks, and we'd love to come up with a better solution. But we get a certain amount of bandwidth that we're allowed to use to the network drive for the amount of data that we store. And unbeknownst to us, for many years, we've been slowly accruing credits because we weren't using the bandwidth. And so that blue line there is how many credits we have with Amazon. And there it is at like 2.2 terabits of credits. So we could read that much data, and they would let us do it at line rate. Wonderful. The orange line is how much we were actually using. And around about, what is that? The 8th, we decided to upgrade the operating system. So we went from Ubuntu 14, I think, to Ubuntu 16. And unbeknownst to us, the default sort of settings for how the NFS cache worked changed. And so we went from hardly touching NFS and having everything in cache to talking to NFS all the time. But we didn't know that. So as you can see, the orange stuff is spiking up, and then the blue credit balance is just slowly coming down, and we don't have any monitoring for this. I didn't know what it was until on the 17th. It took 10 days for us to chew through our enormous bank balance, and then suddenly Amazon were like, oh yeah, sorry, you've used all of your transfer now. We're going to put you at like 14K4 modem speeds now. And anyone who's ever tried to log into a Linux box with like an NFS thing that's like not responding very quickly, it's a miserable experience to debug. And we had no idea, but we thankfully were able to muddle through and work it out. So we fixed the caching, and all was well. There was an S3 outage, and that was fun because Amazon's own uptime indicator of like what's wrong panel is hosted on S3. And so you might think that reasonably you go to that and it would just give you an error. But no, they use CloudFront. And CloudFront caches the last thing it saw. And if the thing does behind the scenes doesn't work, so like I'm refreshing it, like, but it says everything's fine, it must be me. But no, it was Amazon. More recently, we had this amazing fun thing, which Austin was instrumental in helping us to debug and diagnose. And we hit a bug in the kernel where the way that it was handling certain admittedly obscure combinations of things was causing systemd to throw a fit at startup, and that meant that we couldn't do DNS resolution. And it's like the symptom was like unknown host everywhere, and the cause was we were bind mounting something over an NFS drive. I mean, honestly, there's no way you could make this stuff up. It's so complicated. But we got it. We got there. So in the remaining few minutes, I just want to talk about the future, because that's what I'm asked about often. So in the immediate near term, we'd like to change the jailing technique from the fire jail that we use for execution to NS jail. That will fix up some of the issues that people report about not being able to spin up threads in your executing view. I mean, obviously, we're not going to allow you to spin up 1,000 threads. We're not going to turn you into some kind of distributed ray tracing kind of farm for people. But I think it's reasonable for people to be able to make a thread and let it run as well. That seems not unreasonable. And obviously, the bugs need to be fixed. And I would encourage you to file bugs. I know it's sort of slightly demoralizing for me to see the 400 plus open bugs at the moment. I mean, some of them are like feature requests rather than bugs, but we would rather know about them and then we can sort of try and prioritize them and fix them. But again, we're a bunch of volunteers. We tend to fix the things that are most interesting. So I'm afraid some of the more older bugs that are like, yeah, under these weird circumstances on this particular browser, and yeah, okay, no, maybe not. But the main thing I really want to do next year is make it so that it isn't rubbish on a mobile phone. I think everybody here in this room has seen something on Twitter and gone, oh, that looks cool, click, and then gone, yeah, and then you click on it and then the thing zooms in and then you're like, oh, no, I can't get out of it, and then you close the browser. And I can't promise you a smooth IDE-like experience. I can't promise you that, but I can hopefully get you something where you can at least read what the poster intended for simple views. So that the whole golden layout thing is amazing and it's given us that power to move things around, but it's also a curse because the URL you share has to store the layout of all of your windows so that you can say, hey, on the left-hand side I have this, and then I have 3 compilers, and that doesn't necessarily translate well to a very thin portrait view. So we're going to have to come up with something. And there are some sketchings of some native clients as well, so potentially that's maybe part of the solution. But right now I'm just hoping we can get a relatively cut down editor view that doesn't hurt to use, and maybe read-only as well, and then maybe just a drop-down of all of the different displays of it, something like that. And obviously, if you have ideas or if you have skills in this domain, we would really encourage you to come and help us, because everything is open source, and we accept patches pretty much all the time. So, in conclusion, I feel I always have to put a conclusion slide in any kind of presentation, right? What have we learned? Well, I've learned a ton. I've gone from just some rando C++ programmer working in finance to I'm more known than I would like, but individual. So many doors have been opened for me personally. I've spoken with a number of interesting companies. I'm here in front of you right now because of it. I've learned that the C++ community is an absolutely amazing place. A lot with Austin here in the front row. We've got Ruben, Partouf, Chady, Jared. There are just a whole bunch of really core developers, all of whom have the keys to my Amazon account effectively, and I trust them all to not run up my bill too much by playing around with new instances. And obviously their support and the support of many other people who file issues or give me pull requests or email me and say, even just saying, thank you, this is useful. And like the number of professors that email me and say, can we use this in my class? And like, it's just so overwhelming and really quite, emotional. And moreover, thank you all for being here and listening to me talk about my funny little website. There are links here for, I don't know why, because you can't click on them, but there are two GitHub repositories, one that has the code on that you can just clone and type make, and it should just work, TM. Another one which, if God forbid, all of the volunteers were knocked down by a bus and Compiler Explorer went off the internet, you can pretty much reconstitute it from the image repo that has all of our Amazon configuration, it has all of the scripts we use, it has all of the tooling we use. There's a Patreon link there if you want to help with the finance of running the show. And in the remaining 3 minutes, I actually have got time for some questions. So I'd love for you to, if you have any questions, there's a microphone, I think, over with Zoe. And if there's anyone, oh, there we go. Oh, there's one at the back as well. So, but
do compiler developers use your tool?
So, I was going to repeat the question, but I think you can actually hear. Are there any compiler implements here? Do you use Compiler Explorer? There we go. Oh, thank you. Yes. And also, when I was in a sort of a fit of embarrassing, like looking up at this type of stuff, I don't know what the right word is. I've lost the word. I did do a search through like the issue tracker in GCC, and the number of hits that linked to Godbolt was quite a lot. So I think they do, and it's not just. Sorry, remind me your... Clang. Not just Clang, yes. Any other question? Oh, you have a question as well, okay.
So for Clang format, is that done server-side or browser-side?
So Clang format is done server-side. It's actually posted back up to us, and we run it, and then we bring it back. And I mean, and as a follow-on from that, many people suggest using like WebAssembly and sending down like giant globs of like, but do you really want 250 gigabytes of download to run the compiler? I don't think so, but
yeah.
But it's a point actually, and certainly for some compilers, emitting WebAssembly and then running it locally in your browser would be kind of a cool thing to do. So that's, if someone wants a project.
I didn't know you had actually added that. I asked for that like a few years ago.
Oh, you did?
Very, very glad it's there now.
Cool. There's, I think, a question here.
How high are the chances of convincing Microsoft to also support ClangCL on their machines?
Oh, that's an interesting question. I don't know, actually. I think we should probably ask them. I'm sure they would be interested in getting that kind of stuff working. All right, we've got a minute left. Oh, there's one in the front there.
I'm wondering, how do you manage the auto-scaling options and the amount of processes that can run on a single machine?
Very poorly. That's how we do it.
Exactly what I was going to say.
Yeah, Austin knows how the sausage is made specifically there. At the moment, we measure just the load average of the CPUs across the fleet, and once it goes above like 0.3, we keep adding them until it goes below 0.3, and that's not a very good way of doing it at all. Oh, you're doing a pass on the mic so that we can hear him.
And every instance can only run 2 compilers simultaneously.
Yeah. So the instances types that we choose have 2 CPUs. There doesn't seem to be too much point in running more than 2 at a time. And so we use the load average as a sort of very proximate thing. Ideally, we'd have like a queue that was across all of the compilers, and once the queue gets too big, we start adding more workers and things like that, but that's sophisticated stuff, and we're not very good at that. There's one more question over there, which will probably be the last, I think, if there's time.
Any plans to support the CUDA and VCC compilers?
We do support some level of CUDA. I always get confused. I'm not an expert in that domain. I know that we have some level of CUDA. Is it CUDA? Oh, I'm looking at you. I don't know. Yeah, there. Maybe if you could tell me more specifically offline, we could look at it. But certainly we're asked for SYCL. I think people are asking for a lot. And there is in our whatever our CUDA-like thing view is. I think we only show like the intermediate format. We don't show the actual bit patterns that go to the graphics cards. But I am extremely not understanding what I'm talking about right now. I'm using words I shouldn't in front of public, but luckily it's not being recorded or anything, so we should be fine. Okay, I think with that, we're going to have to finish up. So thank you all for listening, and thank you for your time.